Atterberg. Did somebody ask the question? No. Oh, a little notice came up to tell me that this was being recorded. Atterberg limits and natural water content are very useful as a guide to engineering properties, but at least as far as residual soils or volcanic soils, not as a guide to classification. My experience with volcanic clays in Java taught me that the most widely used laboratory classification method, part of Casa Grande's unified soil classification system, doesn't work, or it's not valid, particularly for the volcanic clays. If they're sedimentary clays, then it probably does work. But for as a general rule, you should, I'll mention this again in a moment, you should never dry volcanic soils before you do your Atterberg limits and things like that, because it alters their properties. I just want to emphasize that Atterberg limit tests must be done properly, which means technical staff must be trained and supervised by people who really are experts in those tests. We ran, when the second time was in Bandung, training courses for staff of laboratories that were being set up in the various provinces. Sometimes I did go to the province, and other times they came to Bandung, where I ran courses for them. And as I've said below there, me, a younger version, training engineers and technicians to do Atterberg. That would have been in Bandung somewhere. The courses took place, I think, I came back in '68, so it would have been about 1970 where we were running those courses. And it might surprise you, I've published quite a few papers with Atterberg limits, particularly the paper that Mike mentioned that I wrote when I not too long after I left Bandung, and there are a lot of Atterberg limits there, and in all of my other Atterberg limits and papers. None of those Atterberg limit tests were done by either myself or staff that I trained and supervised, just to make sure that they were reliable, because some engineers are not very diligent in checking on the way their staff do these tests. And if you leave technicians to teach the test, they tend to drift away from proper procedures. So you just need to be aware, as I've emphasized there, it is necessary to do the test properly, but if they're done properly, they are very useful. And they're useful for two things. One is the position of the soil on the plasticity chart, which indicates just what the nature of the material is. What I've said here, it indicates their inherent properties. Then it's the relationship between the natural water contents to the liquid and the plastic limits. That tells you something about the way or the state in which the soil exists in the ground. So let's have a look at that. Now, this is some data I've picked it up from various sites around Indonesia. The ones above the line here, these ones here are all from, it was a couple of projects in Java, which were in the old sedimentary clays, which were sort of shales or hard clays. So they're scattered along the above the A line. You've got some fairly high liquid limits ones there, that one there. Then you come below it. Now these triangles are the red clays, and these dots one come away out here are the volcanic, the allophane clays. So according to the Casa Grande classification system, these ones down here should all be silts. But anybody who's worked with red clays will know they're not remotely like silts, they're really like ordinary clays. And they are very good materials. I'll just come on to that again in a moment. So what I've said here is, in the case of what I've already said, the chart's not a reliable basis for rigorous classification. Red clay and allophane clay are definitely clays, although according to the plasticity chart, they are silts. And note that visual classification using manipulative tests is always more reliable than the plasticity chart. The plasticity chart was based on Casa Grande getting hold of a whole range of various types of soils and working through them all and classifying them according to the manipulative test I've just described, and then drawing a line to divide to separate the ones that behave like silts from those that behave like clays. that's just summarizing the situation in respect to the soils of Indonesia, really. These ones up here will almost invariably be sedimentary soils, particularly the ones that have got a large quantity of that clay mineral, montmorillonite. The red clays sit down here, and their properties are very good. They are excellent engineering materials. Then we've got the Volcanic S1 Stresses out here. The engineering properties of these ones are unusual. They're very good in situ, in place. You can see that from the terraced rice fields that are built on all up and down Java. But if you remind that we mold them, some of them are quite highly sensitive, and they'll tend to become very very weak. So that's how I think the plasticity chart ought to be used as a guide to their properties, not trying to use it for rigid classification. You should do that on a manipulation test, but as a guide to their engineering properties, whether you've got a problem material or not, the plasticity chart is very useful. That's probably the most photographed rice fields and not in Java, they're in Indonesia, and every tourist bus stops so people can take pictures of them. But they are a nice example of the fact that you've got slopes of 30 or 40 degrees, fully saturated, because you've got a canal coming along here, feeding water into here and trickling down here. And even just the slopes between each layer here, they're quite steep, and they've got water retained immediately above them, but they stay in place. They're remarkable soils. And this next one, which Mike gave to me, Mr. Dovey gave to me, and this was somewhere in East Java, and you can see you got a bit of a slip developing here on a very gentle slope. So this, as I've said, the slip failure is on a very gentle slope. It's in East Java, I think not too far from Semarang, if I remember rightly. That the term black cotton got into the literature early because they were studied in the plateau cotton growing area of India, and they were found out to be very highly plastic in containing montmorillonite. So the term black cotton got into the literature. But as I said, they've got rather high liquid limits, well above the A line, and their properties are pretty awful. They split as they did here. Now, the second use of the chart, valuable about the state of the soil in the ground. To do this, we must also know, I've already said, the natural water content. And I'm going to use the term compactness here, or denseness, although we don't normally use compactness or either denseness for clays, but I'll just mention why. With sand, you use relative density as a measure of the denseness of the compactness of the soil. And with clay, we use this thing called the liquidity index, which is the ratio of the plastic limits to the let's wait, and I'll bring the chart up in a moment. It's the ratio of the difference between the natural water content and the plastic limit and the liquid limit. That's what it is. It's the natural water content minus the plastic limit divided by the liquid limit. However, with the clay, the liquidity index does not tell the full story. The liquidity index will actually only tell you what the remolded strength is if you remold it into a softened state. So we also need to know what the in situ undrained strength is to really evaluate the soil. Some clays have a natural water content well above the liquid limit, but that does not mean at all that they are soft. In fact, if they had a water content higher than the liquid limit and you thought that they were okay, they would, once they were remolded, they'd flow away. In other words, if they had a water content higher than the liquid limit, they'd be flowing away. But there are plenty of soils with the natural water content above the liquid limit, quite firm in situ. this is just to emphasize that point. They tell us, or they not tell us, there's plenty of literature to indicate that the undrained shear strength at the plastic limit is somewhere around 200. A recent paper said it should be about 170. And the difference between the undrained strength at the plastic limit and the liquid limit is a factor of 100. So if the undrained strength up here is 200, your undrained with 2 kPa and a little bit left. So if your soil has got a liquidity index, it will be up here somewhere, and it will be sufficiently liquid that it would just flow away. But as I said, there are quite a lot of soils that have got a liquidity index above 1 or natural water content above the liquid limit. And tropical red clays, they generally got a natural water content fairly close to the plastic limit, so they would drop down here. This is some data we've got from weathered sandstone in Auckland. They're around about here. But the volcanic ash clays, they're mostly around here, but you can find the volcanic clays with a natural water content fairly well above the liquid limit. Some of you may be aware of what they have in Norway, the quick clays of Norway, where they've got natural water contents well above the liquid limit. And they had a very famous slide there, I've forgotten the name of it. Mike probably knows it because there's a famous movie. Somebody had this was way back in the 1960s, I think. They had a camera of it, how these big chunks of farmland were sliding down into the lake because they consisted of quick clays with water contents well above their liquid limit and things like that. That's a bit off what I'm trying to talk about. Let's move on to the next one. Yeah, see, this is what we use with sands over here. You've got a minimum void ratio here. You've got a maximum void ratio here, and you define a density index as the maximum void ratio minus the natural void ratio over the difference between the top. You probably learned about that. So that's a measure of how dense or how compact the material is. We use a different index here to indicate the state of compactness of the clay, which, as I said before, is the natural water content subtracting the plastic limit over the difference between the two. So it's this amount here over that amount there. So that's telling you it's telling you that if your natural water content is somewhere down here, that it will not be a sensitive material. It will have a strength fairly close to the plastic limit strength. So it's not going to be a difficult material to work with if you want to do earthworks. In fact, the optimum water content from a standard property compaction test for most clays is fairly close to the plastic limit. And so doing earthworks, you hardly need to do property tests and things because the natural water content is so close to the ideal water content for doing compaction. But if you've got a natural water content way up the liquid limit, you well know from visual observation of the site that it's a perfectly safe material in situ. But if you want to do earthworks, it will be highly sensitive, and you'll have a lot of problems with your earthworks with the elephant clays with the natural water contents higher than the liquid limit. Moving on from this, clay with a low liquidity index is likely to be a strong material without a yield pressure. It will not be a difficult material to excavate and compact, and vice versa. Clays with a liquidity index near the liquid limit may be quite firm in the natural state, but may become very soft when disturbed or remolded. I won't spend time on the situation with the sand, but it's similar. Now, talking about these three types of materials in a general sense, the old sedimentary clays, these are generally of high plasticity and poor engineering properties. They're likely to be prone to swelling and shrinkage, and of low effective stress length, so of quite low effective, the C and the phi are quite likely to be low. Some of you may be aware of slips that occurred on the new toll road between Jakarta and Bandung after you head inland up towards Bandung. There were slips there. They were of volcanic materials sliding on top of the old sedimentary materials, and that's common with some of the very large landslides that you have in Java. It's often the case that your volcanic material is not very deep, but it's relatively shallow, and the boundary between that and the old shales and things is the weak point in it. The water will likely to be held up once it gets seepage down towards the old clays and build up the pore pressures above it, particularly during heavy rain. So that's the most, what would you call them, the most difficult landslides in Java that I know of are generally of volcanic materials slipping on top of the old the old marine clays. The young marine clays I won't deal with. They're very deep, they're very soft, and they're not unique in any way from the young marine clays you've got in Malaysia or Thailand. Now the red volcanic clay, these are the alloysite ones. These I've mentioned have excellent engineering properties. For geotechnical engineers, they're like ideal materials. They've got high strength, low compressibility. They don't shrink and swell. Their natural water content is close to the perfect limit, so very little or no driving is required for earthworks. That's a picture of like Davies, where they're building a reinforced earth wall, and they're working in the red clays that you have around Java. Thanks for that, Mike. I looked after it well. The volcanic ash clays, these are unique, and their properties are they've got very high water contents and very high Atterberg limits. Atterberg, they've got water contents up to 150 or 200%, and they've got liquid limits up to around nearly 200. When dried at room temperature or even in the oven, their properties change, and the change is irreversible. They lose their plasticity and they become like really fine sands or silk, and the change is irreversible. In their natural state, they've got good engineering properties. They're very stable on steep slopes. They've got low compressibility and they don't swell or shrink. But their natural water content may be close to the liquid limit, so they become soft when disturbed and remolded. Earthworks can become difficult. Right, let's move on from there. That's a cut slope in allophane clay, just showing a nice cut at about 60 degrees on one of the geothermal projects. There's a limit to how steeply you can make your cuttings into them. This was an access road to a microwave station on Gunung Tilamoyu, which is a bit south of Semarang in central Java. So they did have a few slips. Fortunately, they weren't too bad, but they wanted to have a very wide road so people could pass up and down, which was quite ridiculous, really. If they'd only built it with a single way, they might have avoided some of the slips. And this is an interesting dam. This is built out of this very unusual clay, although the Dutch didn't particularly realize how unusual it was when they built that dam. 1927 and 28. And the Dutch were a leading nation in soil mechanics, partly because of their involvement with building dikes and things like that. So they built this one out of volcanic ash clay with allophane and things like that, and it's performed perfectly to this day. If you go back and look at the papers about this, you'll find that they were building another dam in a totally different location out of a sedimentary clay, and it was built to the same dimensions. Before they got the sedimentary one built to full height, they had a slip in it, and they gave up that project. But this one here got built to full height and is still in good shape today. Interesting, they've got standpipes in it for measuring the pore pressures, and they've got technicians up there, or one technician who reads them every week, I think, and enters the data into a little book down in this little house down here. So I said to them when I visited this site, and who picks it up to read the data that goes in the book? And he said, well, he wasn't actually sure, but sometimes people come and pick it up, but not very often. And no doubt, well, Mike sent me a picture quite recently. That picture I took was in the very dry weather. You can see that the lake level is very low. This one is a much nicer picture. That one Mike sent to me. The lake is full and it's all very green round about here. Very nice. But it's the same one. This is just going back to that one I showed at the start. If you look here, you can see the layers. Some of these are fairly recent, you see, because this is not weathered. It's like a gritty material. These ones are weathered. It depends on the sequence of the eruptions. You may get a material much more weathered deeper down than up near the surface, which is not the usual case with residual soils. Anyhow, this one I knew enough about these volcanic soils that I could recommend that they put this on a raft, and they put one on a raft. This is the second stage, and they were joining this one to the raft foundation here. There was a possibility that the load coming on here would cause some settlement. My estimate was going to be about 15 or 20 centimeters, which might have sort of caused a bit of distress here. But I was on the site some years later. I asked them if I could go down and have a look at the joint. They took me down and we had a very careful look. There was no trace of any distress. You couldn't see any cracks or anything going along here. So that the settlement is obviously pretty small and not of any consequence. This is illustrating the very strange properties of elephant clay. These are proctor tests, ordinary proctor tests, starting from the natural water content. And each one is a separate sample. If you keep using the same sample, you just do more and more remolding of the soil, and you remold it and change the properties. So each one is a separate sample, and we spread them out on trays. Well, I did, or the technicians did, and we weighed them. So we tried to leave them drying out for long enough that we would get a set of samples, all at different water contents. And then we just simply did, we did proctor tests all the way along. That's how we got this line. And then we did proctor tests at various water contents, mainly after they were air dried and after they were dried in the oven. You see, when you come back along, you change their properties, even by just drying out to this point here, which was still quite well above the air drying value. So if you're going to do earthworks, you want to be very aware of how you do your proctor tests. That if you follow normal procedure, I know there have been problems because the easy thing to do is to dry it back to here, and then you can just add the same quantity of water and turn to get the points. But when you've done that, you've altered it here. So if you write your specification, assuming this is your maximum, or up here, your maximum dry density and that water content, when the contractor comes to try and contact in the field, you won't be able to get to this point. You'll only be able to get to some point down there. So you just need to be aware of that. And now, just for some general comments, the interpretation, how am I running for time? Yeah, I haven't got much longer. I think I started about 5:15, I think.
No, it's okay, Laurie, you're fine. It's good. Good.
All right, am I?
Yep.
The first one is odometer test interpretation. If you are aware of textbooks or you paid attention during your lectures, and you know there's a standard procedure that Casa Grande dreamt up for identifying the pre-consolidation pressure. You draw a line out here, you draw a tangent out there, you draw an interceptor here, and you project this back, and that intersection point there defines the pre-consolidation pressure. Now, and I've got this from 3 textbooks. If you then redraw these curves using a linear scale, you'll find there's no sign of any change in the gradient. So this interpretation here is not revealing anything about the soil property. It's just a feature of the way you've plotted the data. The log scale shows a pre-consolidation pressure, and the linear scale shows no signs of pre-consolidation pressure. And if I move on from there, I had some volcanic materials which were really quite different in their water contents, their void ratio. So I've done these 3 odometer tests. So you would the one of the defects of the log scale is it suggests that the compressibility of all soils has got the same pattern. They come along and they curve over like that. You'll never find, if you plot it on a log scale, that you get anything other than this. So the assumption is you have a certain compressibility here and a different compressibility down here. But if you convert it to a linear scale, the picture is quite different. Some volcanic soils and some residual soils definitely do have a change in strength or change in compressibility here. That should be called a yield pressure, not a pre-consolidation pressure. It's something, it's the point at which the structure, there's a certain structure in the soil that gives it a firmness that it holds onto up to a certain point, and then the pressure starts to collapse that structure and you get a yield going here. So this is called strain softening, really. Well, this is a linear one, and this is what they call the strain hardening, because as the load comes on, the compressibility is becoming lower. So that's a better picture, in my view, to give you an understanding of the compressibility of soils than the traditional one that you find in textbooks. The log scale really gives a useful picture of soil compressibility. And for settlement estimates, the linear parameter MV is much more appropriate than the log parameter CS. So you can get your linear parameter from this graph here. The picture, as I understand it, Mike can probably correct me on this, the English tend to use MV quite a lot, whereas the Americans seem to be stuck with their log parameters. But certainly it makes the parameter itself more reliable, and it makes it easier to do your settlement estimates. You don't have to mess around with the messy formulas there. Yeah, so that's what I've just said. I think that graph there is a far better portrayal to indicate the way soils behave than this one you'll find in a lot of the textbooks. The portrayal on the right gives a much more realistic portrayal for most soils. And just a word about flow nets. This is not particularly important, although in some situations it is. If you determine by sticking down piezometers or things and identify a phreatic surface, the general thing that people do is they assume that this is a boundary between seepage when you've got no seepage, and so they draw the flow net like this. That actually doesn't make much sense, because it implies that there's no rainfall on this slope here. There's only rainfall somewhere away from that. So if you actually do it realistically, and you can do this, I mean, you can do it by hand actually, but I used CW to do it, and you put a uniform rainfall all along the surface here, and that will generate the flow net for you, and it will line in where the phreatic surface is. So all your phreatic surfaces, it's not a boundary below which you have seepage and above which you don't have seepage. Or in clays, I mean, in sands it would be different, because the water will drain out. But in clays, water doesn't drain out under gravity and leave voids behind. It simply flows down through it. And it's not difficult to learn to draw these flow nets by hand. I sort of made myself really skilled at drawing flow nets, because I've always thought of what a wonderful tool they were. But this is probably not particularly important with most slope stability work, because the assumption that there are no pore pressures above here is really a safe one. Yeah, that's right. It's safe because, in fact, the pore pressures above here will be negative. These pore pressures here are positive, but down here they're negative. So if you assume they're zero, when in fact they are negative, you're safe, because the negative value indicates a much higher effective stress on the material above that. But there are situations where, for example, if you had a flat surface and a man-made action was lowering the water table and drawing the water table down, you can't make the assumption that once the water table gets to a certain depth, everything below it is not going to compress anymore, because the further down you draw the water table, the higher will become the negative pore pressure above it, and it will still cause compression above as below. And now a few notes about Estimating slope stability with residual soils. I've already made the point that residual soils, these are mostly just a few pictures to indicate what you've got. I did quite a bit of work in short intervals in Malaysia once, and on a particular road there was some, they were having a lot of slips, and you can see how useless slip circle analysis or any sort of analysis would be with a soil like that. This is a rather interesting one. This was South Sumatra, I think, where they were excavating for a canal. You can see that this is clearly Laha material here, and these are, I think these are ash layers you see, and there's probably ash layers down here indicating the nature of the eruption. You see the lavas may not have reached as far as that. Oh, let's go back to that one. As far as that, but you can see again how variable it is. But although I should say this, that red clay does tend to be pretty uniform. In other words, amongst residual soils that I know, the red clay is the most uniform. So you could measure properties there and do slip circle analysis, but you need to do your laboratory test at very low stresses to get reliable values of C and 5 for this. And you never know, you can never be sure what the worst core pressure situation will be. So you're already stuck with difficulties there. And again, these are from a couple of jobs in Malaysia. You can see here that they've got these planes of weakness or something. And soils have got their own ways of behaving. You would think if you had a weak plane here, it would go up to the surface and all of this material here would come down instead of taking this piece on down here. Anyhow, the people who, they were overseas consultants who decided on the angle here made a very bad blue. They should have had them a lot better than they were. Now this one's rather interesting. This is weathered granite, and we don't have weathered granites in Java, but they've got them in Malaysia. Their main feature is that they're highly erodible, although this is actually a surface slump here. But again, trying to apply slip circle analysis to this is not a particularly appropriate thing to do. Yeah, this is, I can't move this down. I've got it, oops. Hang on, I'll come back here. Yeah, here we are. Measuring the shear strength of C and phi is very difficult. These are arguments about the usefulness or otherwise of analytical methods. Very few laboratories would have testing facilities large enough for the large samples needing to be tested. You'd have to have large samples of these non-uniform materials. And in addition to the strength parameters, knowledge of the seepage state and the slope would also be required if you want to do analysis of any sort. In particular, the worst case seepage state likely to occur during that. That's what you need to know, and that's only a guess. You can make a guess at it, but and assume the very worst state, but it's probably likely to be extra conservative. So we're forced to use non-analytical methods for assessing the stability of natural slopes or cuts. These are visual inspection of the site, determining the geology and the soil types on the site, and then a lot of judgment based on past experience. Those are the sort of things that are important. And this is the site that we looked at before. To build the dam, they had a bog pit, and I think this is the slope of the bog pit. This is the base of the bog pit. But the back slope of the pit was perfectly stable. I'm not sure what was going on here. It looks as if they might have been stockpiling something here that slipped down. But the rear view of it, it had side slopes about 30 meters high and an angle of 45 degrees. And I measured that up quite accurately just out of interest. And then I was asked to advise the company wanting to possibly a site with a geothermal power plant, and they wanted to make a cut in, and they wanted to know how steep they could get away with for the back of the cutting. Well, I said I was pretty comfortable with 45 degrees, but I would like them to just make a couple of boreholes to satisfy themselves there was nothing unusual going on there. So just an example that if you can find a few bits of actual slopes or cut slopes to have a good look at, they are very useful. If you've got a smooth surface like this, that generally means you're unlikely to have slipping. But if you've got a surface that's a bit rough like that, that's the starting, that's the indication that something's gone on there. Visual inspection is the starting point of assessing the stability of a natural slope. This is a site there to Auckland in New Zealand. It's very close to the CBD, but it's never been built on. You hardly need to be a geologist to know that this looks mighty like an old slip. This is the scarp of it up here. That's the edge of it, and it actually moves a little bit. Still moves a little bit, but I'm just pointing out it's very valuable land, and the developers would dearly like to have it, but the geologists clearly ruled it out in the early days of the city's development, and visual inspection clearly shows signs of instability. And this is a slip, which is a sort of a lesson. This is a road going up to, not to Kamojang, up to the Derajat. This was before they were starting the power station. They were just getting underway. And so they cut that cutting there, and it slipped. And I took the picture from this side. Then I went to the other side and took another picture looking back the other way. And you can see here we've got nice tidy layers of allophane clay. But down below it, we've got this very different material and very mixed. But this appears to be what you would call hydrothermally altered material. You get these flows of hot water carrying various types of chemistry through it, and so that's altered that. So it's this is the reason they've got instability there. If this had been all the way down, then they would have no troubles. But again, if diligent geotechnical engineer or geologist had a bit of a look around, if you went over here and went to the other side of this gully here and looked back, there's the cutting over here. And if you look at here, you can see the slopes are not very steep. You see, this looks like an old slip, and this looks quite recent slips. This is telling somebody familiar with the sites that this is not what you expect with normal volcanic ash clays. So it would have been, if somebody had expected this, they might have said, well, let's avoid this and take the road further along the side and follow the contours, so that they wouldn't have had to make those excavations. So this is just about draws me to the end of what I want to say, but I'll just mention something I came across when I was involved with Malaysia some time ago, that a geologist did a very careful survey of all the road cuttings at the time. That published this paper back in 1968, and this paper was in the proceedings of that was the first Southeast Asian conference. And what he did was he went around with a surveyor. Well, they maybe just had an ABNY thing to work out the slopes, but he took measurements of the height of the slopes and the geology, and then he produced a paper with tables and things recommending slopes for the various heights and the various geological formations. And it's a very useful paper. And I think that paper, is still the best guide for determining cut slope angles in Peninsular Malaysia. But now there are a great many more cuttings, many of much greater heights. And in my view, it's surely time somebody did a similar survey. And I think somebody should be doing it in Java, because the advent of all these new toll roads and things are building, there are lots of slopes all around in various materials, and putting together a paper summarizing that, the heights, the angles, and the geology would be very useful for people building more roads requiring cuttings. Just a comment, how to become a better geotechnical engineer. Recognize that geoengineers are not like structural engineers. The latter have control over the properties of the materials they use. steel, concrete, wood, etc. Geotechnical engineers deal with material that is never uniform, so that theoretical analysis is always an approximation. I mean, in many cases, it may be a good approximation. In other cases, it will be a very poor one. Geotechnical engineers must always judge the reliability of the information they are using in their theoretical analysis. And they will only be able to do that if they, number 3, spend less time in front of a computer and more time in the field observing, testing and sampling, and more time in the laboratory also observing and learning how all the important tests are done, ideally learning how to do them yourself. That brings you to the end of my presentation. So thank you all for your attention. If you're still awake, thank you for that as well. And I'm happy to listen to any comments or questions that you may like to put to me.
Okay, so Laurie, first of all,
hello.
Yeah, there's a round. We can have applause now.
Thank you.
Online
Don't overdo it.
Yeah. Laura, I hope if you can hear me clearly, that was a really wonderful talk, full of a huge amount of information and advice. We already have one person saying, permission to ask, can we get the material? So with your agreement, if we can provide a PDF copy, probably 2 slides per page of your material, is that okay?
Oh, look, I sent you the
Yep.
PowerPoint. You can send a PowerPoint to anybody.
Okay, that's very kind, lovely. Okay, that was one question which we often get. But no, certainly. So to all the people who are listening in, we will circulate a copy of the material from Laurie's presentation. So many important lessons there. Another question from Elizabeth Saragi. What causes red clay historically?
Oh, yeah, I forgot to explain that. The red color isn't actually due to the presence of halloysite. It's due to the presence of iron oxide. That the weathering process, the trickling water has got various chemicals in it, which dissolve most of the silica. So the silica content and the silica based clay minerals tend to disappear, and you're left with these concentrations of, they call them sesqui oxides. I don't quite know, but they're like aluminium and iron hydroxides rather than oxides. And it's the iron oxide that's left behind that is giving the red color, as I understand it.
Thanks, Laurie. Okay, so we have a comment here. Enrico Winata says, good presentation, Laurie. Thank you for sharing. So you don't need to answer that, but all I can say is that I agree thoroughly. Actually,
I should explain,
yeah.
Mike, I should explain also that much of what I've given here is in the last chapter of both books. There's an additional chapter that I put in the fundamentals of soil mechanics. There's a chapter there on the geology and soils of Indonesia, which covers a lot of what I've gone over tonight.
Okay, well, thanks for that reminder. That's wonderful. Oh, yeah, the Norwegian landslide, the quick clay one was Rissa. Although
yeah, that's right.
I had to Google it to just find out. I remember that name.
Yeah, it's a wonderful portrayal of the usefulness of Atterberg limits, because all they did after that was go around and measure the Atterberg limits and the water content and decide which ones were high risk and which ones were low risk. Yeah. Yeah,
no, it's worth watching the video, even with interesting commentary in a very English kind of English. It's quite good. Yeah. Let me see. Actually, I have a question for you, which I may have asked before about the red clays around Jakarta. What interests me is that they're quite thick. I mean, I don't know the thickness, but let's say it could be 20 meters, 15 meters, something like that, which seems to imply that a huge amount of volcanic material has made its way northwards from the volcanoes. And knowing the volcanic activity over, say, the last 1 million years, there haven't been a huge number of eruptions producing vast amounts of ash. So I can only assume then that the total thickness must be very old. The lower part of it must be extremely old, because to build up, say, 20 meters of volcanic ash from occasional eruptions would take a very long time. So I've always been slightly mystified by the situation of just how old and how long ago the ash got there that's now turned itself into the red clay that the Tanamera that we like to make use of in our highway cuttings and so on.
Yeah, so you're right. It must have been subject to the same sort of weathering at the surface that goes on now. And that must have, I suppose, the sea levels rose or the land went down, but it must have been at one time subject to open air and rainfall to produce the weathering processes that convert it to the red clay. But yeah, I don't know any more about the sort of the geology or the changes in the changes in the sea level in relation to the land mass. I don't know. You would think it would have to have been the land surface at one time.
Yeah.
That's about all I can say about that one.
Thanks. Yeah. Yeah. I just anybody in the room like to ask a question? Yes, we have a question in the room. Yeah. Yeah. So just if you guys like to give your name and ask Laurie the question.
Yes, Laurie. My name is Alexander Pian. Pleased to meet you. And I have a question about the seepage that you explained about the volcanic ash clay. You mentioned that the groundwater is, we have assumptions that below the climatic line, right? So in the terms of the permeability testing, which one is more valid? I mean, we're talking about the clay behavior when we are testing on the lab. Do we need to saturate the clay first? Or we going
look, I'm sorry, my hearing is not too good. I didn't quite get all of the question.
Okay, sorry, Leslie. So talking about the volcanic ash, clay, and you explained about the phragmatic lines that in the theoretical that the phragmatic the water is going flow below the phragmatic lines, right? So in the terms of permeability testings, the valid testing result is it we need to saturate the soil first before we conduct the real permeability testings. That we may as you explained that the phragmatic lines above the soil above the phragmatic line has the negative pressure. Thank you.
So
yeah, I'm not quite clear. The phreatic surface doesn't indicate that the material below it is any different to the material above it in a clay. In other words, in a clay, you've got a zone which is fully saturated for a long distance above the phreatic surface. So it does. All you've got is a gradual change in the pore pressure from maybe highly negative up near the surface, and the pore pressure just steadily increasing with gravity. So I don't think the phreatic surface would actually indicate any change in properties of the soil. The thing that would indicate changes in properties is the depth to which it's not fully saturated. There's a zone further up where it's not fully saturated. You do have different chemical things going on, but I'm not sure if I've got the question right. Does that answer the question?
Laurie, also sorry, it was also a little bit about if you're going to measure the permeability, would you recommend that you need to saturate the clay first? Is that correct? Yeah. Do you need to saturate the sample before you measure permeability, or attempt to measure it partially saturated if it is partially saturated?
Well, most of the clays that I've ever been involved with, once you're down about well, sometimes it's not very far at all. Only a few, only 20 centimeters or something. They're fully saturated. So I wouldn't think there'd be any need to saturate them. You should be. Most projects I've been involved with, some of the research I did, you'll find it in that paper that Mike mentioned. And I measured, I got information over considerable depths in volcanic ash clays and in red clays. They were fully saturated up to within a very short distance from the surface. They were fully saturated up to, I think by the time you were down a meter, they were fully saturated, and the ones above were so fully saturated you didn't have to take account of the fact that they're not. So if your sampling is done properly and your sample preparation is done properly, normally I would expect you to be testing a sample that was fully saturated. But certainly if your material is partly saturated, you would have to fully saturate it. I mean, you could still do that by what they call when they're testing triaxial samples, using back pressure to get them fully saturated. If they're partly saturated and they're genuine clays, it takes an awful lot of time to fully saturate them just by running water through them. I think that's my answer.
Yes, I think that's a very thorough answer. Thanks very well. I don't see any other questions from the room, or can we let? Oh no, David Mead. He's got another geotechnical question, I think, coming up.
Yeah, actually, I'm a hydraulic engineer. I've been working on liquefaction project in Palu. It was interesting to see the rice fields at almost a 45-degree slope. But there we had rice fields at a less than 5% slope. So what is it about the composition of soils that could make a slope of 5 degrees liquefy and engulf the population of about 100 houses? Is it a lack of clay and a high water table that might cause such a liquefaction?
What was the dimensions of the slope again, or the slope and the height?
The slope was about 5 degrees for about 400 meters. It had rice fields on it, so it was saturated by irrigation. And yet the slope was only 5 degrees, and yet it liquefied and engulfed a series of houses, killing a lot of people. And I just wondered if there was a sort of unique mix of materials from lack of clay, a lot of silt and a lot of sand that caused such a liquefaction.
Yeah, that's a bit of a hard one, isn't it? Sounds more like the Norwegian quick clays that failed on a very gentle slope. Have you got any tests on it? Has it got a natural water content up near the liquid limit or whatever? Like, have you got any data like that?
There is a fair amount of data by now.
Yeah, there is a lot of data.
This is
from
Palu,
the Japanese.
Palu.
This is Palu. It happened in 2018. There was an earthquake. It was an earthquake that caused it. So there was earthquake vibration involved, as well as a high water table and perhaps a combination of soils that made the slope very unstable. Maybe it was not clay at all. Maybe it was some
fine sandy material or something.
Yeah, I think it was absolute lack of clay. I think it was a high load of silt and sand that was very susceptible to liquefaction when you had the vibration of the earthquake.
Yeah, yeah, I would think that's right. That it's not got a strong structure in it at all, and once you have an earthquake, it would tend to liquefy, all right?
Yeah. Okay. Thanks. Yep.
Okay. No, I think I don't see any more. I think, well, it's probably about time you went to sleep, isn't it? Getting a bit late there in Auckland. Just for those who didn't realize, I mean, Laurie's talking from Auckland, and Auckland's 5 hours ahead of us. So Laurie's doing really well. I hope you remember to have your dinner earlier on.
No problem.
And I'd just like to finish off this sort of electronic part of this meeting to thank you again so much for sharing all your wisdom and knowledge and experience, and the information in your slides. I think people will be very keen to read that again and to listen again to what you have to say, because I mean, there were so many good lessons in the presentation material and in the way you talked about it. And I think the get out of the computer, get onto site is some of the best advice we can have for young geotechnical engineers, because if you don't see things on site, you just don't learn. And so important, especially when site investigations are going on. So I think all that wisdom of yours and all those comments you made are absolutely vital for especially our young student engineers, and I think quite a few of them will be listening tonight. And Laurie, I think we'll let you go now. Go and have a well-deserved sleep tonight. I hope you get your full 8 hours in and can wake up a bit later than normal. And greatly look forward to being in touch with you. I'll be, for other reasons, I'll be in touch with you anyhow in the next few days and so, but looking forward to that.
Yeah, I have high hopes of coming to Indonesia next year. That's what I keep.
Good. Well, if you can, we'll be welcoming you. We'll be very pleased to see you here again. Fantastic.
The problem is I'm getting old, you see. If I don't come to Indonesia soon, I'll be too old, or the cost of insurance will be too high or something like that. But I would really like,
we're all getting older.
Yeah. So thank you to you all for coming and listening. It's been a pleasure. As you know, I enjoy coming to Indonesia, so it's nice to talk to you all. And yeah, if I do PowerPoints or any sort of presentations, I always say people can share them to. There's no copyright or anything like that. You can just share them to anybody. The sad fact is, actually, I'm not going to be around for all that much longer. So I might as well share them around now, but I still already can. So thank you very much, everybody.
Thank you, Laurie, and we will see you back here maybe next year, hopefully. You can possibly.
Hopefully.
Yeah.
Thank you, Mike.
Okay. Bye.
Bye.
Thank you, Laurie Wesley, for your excellent presentation, and thank you also to Michael, Dobby, and David Me for guiding the session. Ladies and gentlemen, we have now reached the end of the event. Once again, thank you for your participation. We hope we can see you at the next event. At last, good evening and stay healthy, everyone. Thank you.
Okay, yeah, right. Those here, time for curry. I don't know if everybody can hear me saying that. And to all participants, thanks very much for joining.
What was the maximum number of people you had listening in?
About 56, I think. So we're going off air now.